Recall our uniform motion ball rolling from a few lessons ago. At time 0, the ball is at the start. At time 1, its position or location is 20 centimeters to the right. 2 seconds, it's at 40 centimeters to the right. At 3 seconds, it's at 60 centimeters to the right. At 4 seconds, it's at plus 80 centimeters. And at 5 seconds, it's at plus 100 centimeters, or 100 centimeters to the right. A data table for this ball would look like this. If we take this data and graph the data as a position time graph, we would end up with a graph with a straight line of best fit. If we look at this graph, it shows us that at each second the ball moves plus 20 centimeters in distance and position. It displaces to the right 20 centimeters each second. The speed is 20 centimeters per second, and the velocity would be 20 centimeters per second to the right. Since the line of best fit is a straight line, we can calculate slope. Slope is rise over run. And if you look at the graph, you can see that rise is position and run is time, so slope is position over time. The unit for rise is centimeters to the right divided by time, which has the unit seconds. Centimeters per second is the unit for velocity. So slope equals velocity. Let's use the slope equation to calculate the velocity. Slope equals rise over run. Rise is change in y, which is y2 minus y1, and run is change in x, which is x2 minus x1. From our graph, we can choose any 2 points that are on the line, which in this case are all the points, since the line passes through all points. If we choose to rise from 40 to 80 centimeters, then we must choose the corresponding times, 2 to 4 seconds. Delta y is 80 minus 40, which makes 40 centimeters to the right. Delta x is 4 minus 2, which makes 2 seconds. Slope is 40 divided by 2. That calculates slope as 20 centimeters per second to the right, or simply plus 20 centimeters per second. Let's see what we get if we use the velocity equation. In this case, we do not need to use average velocity, as this is theoretical data and the data points are all perfect. Velocity equals change in position over time interval, which equals velocity final minus velocity initial divided by time final minus time initial. If we choose these two blue data points, which live on the line, then the formula becomes 80 minus 40 centimeters to the right divided by 4 minus 2 seconds. This calculates to 40 centimeters per 2 seconds. We get 20 centimeters to the right per second, or simply velocity is plus 20 centimeters per second. This confirms that a slope of a position time graph provides us with velocity.